let's go into the Python part of this course. So shapely and geometric objects. Most of you now have this open in CSC, but if you don't, you can either launch the student binder. If CSC doesn't work, it will launch for a few moments. I'll start working here in my CSC notebooks instance, which hopefully is still awake. Yes, it is. Should I somehow optimize this? Zoom in a bit more. Okay, so geometric objects, points, lines, and polygons, and maybe even multi-polygons or geometric collections. So basic building blocks of geographic information that we need in order to do spatial analysis, map data, do overlays, and so on. So here we are of course dealing with vector data, as we will be for the most of the course. Then in the last week we'll do a bit of analysis using raster data. And we'll start by focusing on shapely. Later on in the course, mostly GeoPandas will handle the geometries, but it's good to understand what actually happens with the geometries then a bit more in detail. I have here open the Shapely user manual. Some of the links might be broken in the notebook. I'll fix those later. So Shapely is basically a Python package for dealing with geometric objects. So here, maybe I'll draw here. So if we have a point, or then we have a line, or then we have a polygon. So these are geometries. They are not yet kind of geographic data because we don't know the projection, but there are some kind of shapes which then have different kinds of properties. You can imagine that a polygon might have an area, a line might have a length, a point, well, it has at least the location of the point, and so on. Maybe one technical detail to know about Shapely is that it's kind of implements a GIS package, which is then written in C, and there will be, maybe next year we will update the materials to use PyGeos, which is kind of for a similar thing, but then it's more efficient when it comes to dealing with geometries. But GEOS is kind of the functionality behind the Shapely package. And there's then of course different requirements and different attributes and different methods related to these objects, and we'll start learning how to interact with these a bit more in detail. Another new, I think it's a new concept. So a tuple. I hope I'm pronouncing that right. So we'll be using coordinate tuples, so pairs of coordinates, to tell Python the locations we want to use. So tuples are a bit like lists, but different. So it's a collection of elements. It can have two items or even several items. But the main difference between tuples and lists is that you kind of can't change the tuple. You can kind of remove it and replace it, but you can't replace the values. It's immutable. Vice versa, then a list, you can, for example, delete one object from the list and so on. So tuples have these kind of round brackets, while then lists have these, how do you call them? Brackets. The other types of brackets around them. Okie-doke. So in order to start working, we of course need to import Shapely, and often when importing Shapely, we don't import the whole package. We can import only those objects and tools we want to use. There we go. So we do from Shapely geometry import point. I could start with that. I think you have this line of code already written in there. Point would be nice. So what I'm actually importing here is kind of a data type. So shapely.geometry.point. If I would just import Shapely, I would then have to call shapely.geometry.point, which is a bit clumsy, so I'm directly importing point as a convention. So then maybe it's a good thing that the internet connection is super slow, so I won't be going too fast at least. So basically, when we are then constructing points, we are calling the point constructor, and then we give it a pair of coordinates. You can use the same coordinates that I am, or then you can create some other types of points you can test around. So x and y coordinates by default. It can be whatever, it could be whatever coordinate reference system we don't yet know. These are just kind of abstract geometries. And then I'll just go ahead and copy paste that. I'll create several points so we can use these variables then later. I'll just change the input values. Let's see if this should work. Change to something minus. Now, of course, you can have minus values depending. So if we are dealing with decimal degrees, you could have the minus 60 as a coordinate value. But then in a projected coordinate system, often that's not possible. This is extremely slow, the internet, but I'll try to fix it during the break. Minus 2. Okay, so I'm generating several points so I can then use them later on to generate the other types of shapes. And then finally, I can also make a 3D point. So of course, we can have a point in space, but then it could of course have, for example, an elevation value there. I don't know if your internet is as slow as mine, but this is a bit annoying. So I'll do the same point, but then with different coordinates. Okay, well, I'll run that. Hopefully it goes through. Okay, so at least it seems that it went through. Now we have some point objects stored in these variables. And then if this collaborates, you can just call the name of the variable. I'll change my internet connection soon. Is your internet as slow as mine? No, okay. Okay, so that's there. So this renders the actual shape. But then if you print it out, you can already try while I'm waiting for this internet. You see the actual kind of text representation of the point. So it's not more complicated than that. You can of course then check the contents of the other variables as well. Maybe we can check how this point tree looks like. So if you're doing a 3D point, the Z letter indicates that there is actually the third dimension in there as well. Okay. Then the shapely objects have several attributes. Maybe we'll do so that we'll have to break sooner, and I'll fix this connection because otherwise we won't get out of here until midnight. Just to show this one thing. Okay. So if we take, for example, point 1. Okay, so if you check the data type of this point, you'll see that it's shapely geometry point dot point. That's a bit kind of verbose way of explaining the data type, but that's how it is. So it's indeed a format based on the GEOS C++ library that's running in the background, for example, in QGIS. But then there's a kind of handier way to check the data type of shapely objects. So if you have a shapely object, be it point, line, or polygon, if you do .geom type, so then that's an attribute of that object. So then you'll get a shorter version. And this is, for example, a trick you'll need in the exercises. So if you have some inputs, you need to check the data type, and based on the data type, then you might do different operations in the following points. I suggest that we now take a 10 to 15 minute break. I'll fix my slow internet connection so that we can then get this lesson done with. So let's continue at 1:30 if you're fine with that. Okay, let's continue. I got my internet working by just closing everything and starting a browser window. So hoping to speed up a bit. But so far we have defined some shapely points. just giving coordinate pairs and then one point with kind of 3D third dimension, and then we printed out the points, check the data type, and use this attribute geom type to check the data type. So there we have a point in Python, very basic element for doing GIS stuff. We can have a bit deeper look into what different attributes we can extract from these objects. So this code cell is again probably readily written for you. So then if you would call point object dot chords and store that into a variable, can run that cell, so it prints out a bit more abstract information. So it's some kind of coordinate sequence object. And the data type of that is a coordinate sequence. Of course, we would be then interested in the actual x and y coordinates. So let's see how we could get those out of this coordinate sequence object. So first we put coordinates into a point, and now for some reason we would want to get them out. So for example, sometimes you might have a shape file or some spatial layer, you do some stuff in GeoPandas, and then you might want to print out a CSV file with one coordinate for x and one coordinate for y. So then you might have to do something like this in the future, just to give an example of why this is useful. So we have this point chords variable in memory after you have run this cell. So it was points.chords attribute. So we can start working with that. So point chords variable, and then that has an attribute called xy, which we can store in a new variable called xy. In the same way, we could get these x and y coordinates directly from the original point. So point 1, for example, I have in memory point.x, point dot y. I have them there. I'll run this cell, zoop, point 1. There we go. So I had this point chords, which was the point 1.chords.xy, so I get x and y, point.x, I get the x coordinate, point.y, I get the y coordinate, and then there's a cell for printing out this information. This is now a bit even too much zoomed in. I don't know, you can see all of these at the same time. There we go, if somebody's still typing. So the first one, xy, it kind of prints a more complex view. So this is actually, I briefly described what is a tuple. So you can see that there's these outer brackets, then a comma, and then there's one object and the second object in this tuple. So this is a tuple of NumPy arrays. So there is an array of the x coordinates and array of the y coordinates, which came from this point chords.xy, and then I have the x coordinates and the y coordinates as a floating point value. So different ways of accessing these coordinates then once you have the shapely object defined. Any questions here? This might be a bit cryptic. We haven't talked so much about NumPy yet, but NumPy arrays are kind of like lists. Again, like Pandas series are a bit like lists, but smarter. You can think of it as a smart list inside a tuple. Okay, some other then more advanced things we can do with points. In the beginning, we defined here, I'll scroll up a bit, so at least I defined several points. I have point 1, point 2, point 3 in memory. Hopefully you have also several points. defined. So then here under point dist, just double check that I have my recording on. So I'll start with 1 point, then function distance, and then the second point. So the distance function would return the distance between two objects. So me dot another one point dot, then function, and then parameter the other point. So here this is of course some abstract units, but we can then decide, or if we know that it would be in VGS 84 decimal degrees, or if we would know that it's in a metric system, then we could say that the distance is so and so many units, depending on the coordinates. So distance between 2 points. Okay, any questions about points? Maybe I made my point clear. Line strings then, of course, it's one line requires at least 2 points by definition. So this is not a line because it's only 1 point. Then of course one line could have, that's then one line, we can have more than one. So at least 2 points makes one line string. And then now I remember that I didn't, sorry for jumping up and down, but in my very first from Shapely import point, I only imported points. I also want to import some tools for working with lines. So I will import point dot and then comma and then also line string in there. And I need to rerun this cell. So from Shapely import point and line, and now I can access this Shapely geometry line string after importing this. I hope you got that. So line string capital L capital S. I'll scroll down to where we are making lines, and as I said, line takes 2 points, at least 2 points as input. So we can call this line string constructor in a way, and then we give a list. So list brackets, list of points, point 1, point 2, maybe I'll start with 2 points. I'll just remove this for a while just to run that, check that it works, and print that. So I have one line. I can then add, for example, point 3. I'll run that. Now I have line with three points defined. And these are now Shapely point objects in a list. So the line string takes only one parameter, which is a collection of points. So I have a list of Shapely point objects. It's also possible to define a line using a list. So again, it only takes one object, so it's a list of tuples. So I could then just write some coordinate pairs in a list. So what do we have? 2.2 and 4.1 is the first coordinate tuple. Then the second one is 7.2 minus 25.1. You can also invent some other coordinates. This is just making the same line again. 9.26 and then minus 2.456. Okay. I'll name it line 2, not to overwrite that. So I have line string with point objects and then line string with a list of coordinate tuples. So many different data types in there. And as you can see here, as I use the same coordinates as in the original points, I get identical objects. I guess that's quite clear. But depending on the inputs, you might then use either of these approaches for making a line. Again, to save some time, this is already, you can just run this cell. So if we check the type, it's shape, geometry, line string, or then if you do line.geom type, you get this string format line string geometry type information. So then similarly as with the points, you can get line xy. So the line object dot xy, and what does that bring us? So it's again a tuple of NumPy arrays, but this time we have all the x coordinates in the first list and all the y coordinates in the second list. If we check from here, there was xy, 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 so 2.2, 7.2, 9.26 should be the x coordinates which are in here, and then the y coordinates of the line object in there. Then with lines, if we then want to get kind of the individual, what is the x value of this point, for example, or what is the x value of the first point in the line? So we have this lxy variable now in memory, lxy, and it was a tuple, so kind of like a list. So it has two objects, index 0 and 1, similarly as with lists, and we can access the first item, so kind of this first array using lxy index 0. So it's lxy is this whole tuple, and then lxy at position 0 is the first array in there, and then similarly at index 1 should be then the y coordinates. So then you have a NumPy array if you would need then only the x or y coordinates for some future purpose. Any questions about this? No? Okay, then line length. That might be useful. You'll actually need this in the exercise. So it's quite logical. We have the line object in memory, line.length. And then centroid of a line might be useful as well. Centroid. Let's see what is there. So there might be some bracket missing. So these basic attributes then with lines, line.length, line.centroid. You'll get the length in the units, whatever the units are. This is now a bit arbitrary length, and then centroid of the line is 1 point, which is then again a shapely point object. So you might then be jumping around between these different shapely object types when working with then lines and polygons and more complicated objects. Okay, so then off to polygons, unless there's some burning questions about line strings. We'll be practicing these in the exercise. So Polygon here, at the point here. So a polygon needs at least 3 points. So you can't make an area with 2 points, you need at least 3 points, which is quite logical. So 3 coordinate tuples. A polygon construction is a bit, well, it's not that different, but maybe a bit, requires a bit more attention. So we need the polygon constructor, which we haven't imported. So again, I scroll up, sorry for going back and forwards. I will still import polygon from Shapely geometry. So now I'm importing point, LineString, polygon, capital P. As you remember, it's good practice to import the modules you need at the top of the code. You can of course import them along when you're doing the code in Jupyter notebooks, but it's good practice to have them at the top so you see immediately what dependencies your code has. I run this so that I have the tools available. Then I scroll down under Polygon. So Polygon, inside the brackets, again, it takes only 1 input, so there's a list of at least 3 points, so at least 3 coordinate tuples. So let's add those. We can use the same points as previously. 2.2 is the first tuple, comma, sorry, that was the first x coordinate. 4.2, 2.2 and 4.2, then 7.2 minus 25.1, that's the second one, and then I have a third point, 9.26, and then minus something, 2.456, that was our point 3. I'll add some white space. There we go. I'll just, for demonstrating, I'll now delete this poly 2 for the time being. I didn't get any errors. I can check the shape, so it's some kind of a polygon. And then if I would print the polygon, so I see polygon and then the kind of corner coordinates represented like this. Okay, so this is quite easy and intuitive, but of course, more often we might have existing shapely points and we want to make polygons out of those. So let's try to redefine this polygon by using shapely points, and we have those in memory. So we have poly 1, poly 2, point, this is too late for me, point 1, point 2, and point 3. Those exist. And now, well, I think this makes sense. We have a list of shapely points. We could make a line based on list of shapely points, but what happens in here? So here I get an error. Gone. That was because of wrong name. So now object of type point has no length. Maybe, well, this is, but I get a type error. So something is wrong with my input in this case. So for one reason or another, the polygon takes only kind of coordinate tuples as an input, or pairs of coordinates. So we can't give the polygon shapely we cannot give a list of shapely points as input, but we can kind of on the fly get the x and y coordinates of these points as an input. So this part is now a bit tricky, maybe the trickiest part of this lesson. I'll do so that I'll just type it in and then let's spend a moment reading it through. So we'll use a list comprehension to get the x and y coordinates for each point in the list. We have used this maybe once in some kind of extra advanced additional notes in period 1. List comprehensions are quite handy. They're a bit like tricky to read. List comprehensions are basically like one-liner for loops combined with lists. So let's see what that means. So bottom line is that we want to have kind of pairs of coordinates as input for the polygon. And how it goes is that for each point in the list, we want to get the x and y coordinates. And then we want, as an output, we want the whole thing to be yet another list. So I would put these kind of list brackets around this sentence. And then, so what to do for each point in the list? I want to get, you remember that with shapely points you can call point.x to get the x coordinate, right? And point.y to get the y coordinate. We did that previously in here. Kind of as the first thing when my computer was still slow. So you can, if you have a shapely point, you can call point.x, which returns the x coordinate. So back again here. So for point in list of points, oops, no, sorry, I have too many brackets. So this for loop and the list is inside brackets, and then I have another collection for p.x and p.y. I'll just leave it there and run it. Let's first check that the syntax is correct. And it seems that we get a similar output than in there. I think we'll need to discuss this a bit more in detail. So what I will do, that I'll take everything inside the Polygon thing as a separate code cell, and we can discuss that in a bit when everybody has typed this in. So if I only run the inner part from there, what I get is a list of lists. I could also do a list of tuples, which would be maybe more correct in terms of the kind of more matching to the previous one. But in terms of rendering the polygon, it doesn't matter. So I can have kind of list comprehension producing a list of lists, or list comprehension producing a list of points. So what it does is for each point in this list produce a tuple or a list containing point.x and point.y, and then put all of those in another list. Does it make some sense? Maybe yes. So then list comprehension Python. I think we have there. So under data structures, let's see. List comprehensions. So you can imagine that if you're doing a for loop for x in range, do this. So you can then turn that syntax into a one-liner using the list comprehension. So then you kind of read it in a bit different way. Maybe yeah. To what extent are you following the list comprehension thing? Maybe like if you get it complete. Okay, I'll let it sink in. I can share the documentation and maybe some other examples about it, but that's just to highlight the fact that we can't give a list of shapely points for a polygon, we have to have a list of coordinate pairs, so either in a list or tuples, and this is one way we can achieve that. Maybe now I closed my Shapely documentation, but Shapely user manual. And then Polygon. There we go. I think we have one example here. To close my Polygon. Well, why we need to do this is said here. So basically, the polygon constructor takes two positional arguments, and the first one is a sequence of point tuples. So for some reason, it does not take shapely points as in. Okay, maybe let's continue from here. List comprehensions, you don't need them as such during this course, but it's sometimes a handy way of doing things kind of with a short syntax. Any questions about this? Yeah, no. Okay. Okay, but you'll have to, in the exercises, there's an optional task for considering input, which is a list of shapely points, and you can practice this approach then there. Okido. So what else with polygons? Again, you can check the type, either using the familiar type function, built-in function type, or then this attribute shapely object dot geom type if you want. Okay, so we already opened the polygon object help, so you maybe got a glimpse, and you can imagine that polygons are often then more complicated than this. So you could of course have like a polygon within polygon, why not? And of course more complex polygons, so then there's a bit more to polygons than this super simple example. And maybe to continue from here, so as mentioned, polygon takes two arguments, so there's the shell, which is kind of the exterior, and then you can also give input for holes. So if there would be something that only this part is your polygon, it could be a building with some inner yard, and then this one doesn't belong to the outer polygon, so then you can define also the inner hole using yet another set of coordinate tuples. And again, you can access the same help through Python by running this line. I now commented it out because it's quite a lengthy description. So here, just to remind you, you will be reading these documentations, Googling for documentation when you're trying to figure out what all can you do with these objects. Let's check one example of how to build something like this. So there's one list of tuples for creating the world. So it covers kind of the coordinates of the globe in VGS 84. And then there's another list for creating kind of the inner hole. So there could be several holes, so it's a list. There could be several lists of coordinate tuples, so we're kind of putting things into other lists and lists of lists, but here we only have one list or one hole defined. So you don't have to type this in, you can just run the run the cell, and maybe we could, if you want, you can print out world exterior. Yeah, so that's still the list. So let's now construct a polygon based on this list, and maybe you could start doing it. I'll type it in here in a minute. So based on what we have now learned, you can start creating a bounding box for the world. So it starts by the polygon constructor, and as I already have the list there, so I can give this world underscore exterior. So I have a list of at least 3 coordinate tuples in there. It could be a good idea to, I'll just copy it in the cell above just to test it. World. So if you do this world equals polygon world exterior, you should get a box, and you can imagine that it covers the whole globe. And then if we want to put the whole into this polygon, you can create another polygon object. And now I have to check the documentation. So there were 2 parameters. There's the shell and the hole, so the exterior and the interior part. So what this actually kind of behind the scenes, you're actually doing this, that shell equals world exterior. So the bounds or the exterior of my polygon is the world, and then world exterior. And then the second parameter, holes, so there could be more than one hole, is then hole. So now it's the kind of external points minus the inner points. So the polygon is this green area there. So we have a frame around the world in here. You can also print the coordinates there. So now that we have a polygon with a hole, then of course it gets already a bit more complicated how the actual geometries are represented in Python. And then you can imagine if you have the polygons of countries in the world, that's quite a mess if you print out the actual corner coordinate points in that polygon. Okay. Did everybody get this? Can I continue? Mm-hmm. Yeah, question.
Would you not be able to just replace when you have the world as a whole equals, or can you just use the new variable world since we defined it as shell? So now you're just rewriting the same thing.
You mean here?
Yeah.
Yeah, I could put it in there, but if I want to, let's say I would want to, after running this cell, if I want to print world, I want to have that in memory, so that's one object, and then I have another object, this one. So then I could of course like just put it, if you mean why didn't I put it in here, is that like, what you mean?
Could you put the variable world into the world as a whole new variable instead of saying
we
shell?
can try.
Because it didn't work for me.
Yeah, and that's related to the previous example. So you remember that the polygon, this will give, what does it give, an error? Did it give you an error? No.
No, it just gave me this.
Okay, well this is interesting. Apparently it can then, yeah, I'm not sure why it does it like this, but I would stick to the definition that the shell has to be kind of a sequence of point tuples, and it doesn't say that you could have actually a polygon object, but then why doesn't it give an error? I don't know. So that's a very good question. I would assume that it just errors out. Like if I would now do, I'll just copy this in here, world test. Okay, so apparently I'm able to give a shapely polygon as a parameter, but then for some reason it doesn't hold. Yeah, I can look into that, but there's something definitely going wrong in here. So by definition I would then give, as we are giving the kind of list of coordinate pairs, so that at least works. I can dig into this if there's some surprising thing we can learn from this thing. Yeah, sorry.
We'll make it also a polygon object. So we are
Yeah.
test at least.
Did you test that? But because this is like, we could, well, maybe you try it and let me know if it works. Let's do that. That might work. Yeah, but a good question. Great. Then still a few more attributes available with polygons. So let's work with the variable world. I'll just define, there's then the following code cell will print these results. So we have world.centroid, quite logically, world area equals world.area, world, so B box, so bounding box, the bounding rectangular around the world should be equal to world itself. Bounds, but this is quite useful often if you want to, like, you give somebody the bounding box of your area of interest. So shapely polygon.bounds, then exterior of the polygon world ext equals world exterior, and then world ext length. Now I'm calling this world dot exterior. We'll print this out soon and see what that actually does. So notice here I'm calling the attribute length from this previous object. Let me know if I type too fast, or then check from your neighbor. You can print the next. Ooh, there's some Gendroid word. Okay. See, people still typing, but I assume that you maybe got the first two, area and centroid, so I'll scroll down a bit. So world centroid, based on the kind of box we created, it's quite logical. It's 0, 0, makes sense. Polygon area, that's again some arbitrary units, but can calculate the area. Of course, when we calculate areas with geographic data, it's always good to project the data into some known projected coordinate system, and we'll do that next week. Bounding box, we had a box-like object, so the bounding box is equal to the shape, but of course if we have Finland, then the bounding box will be like the max-min coordinates, which is then a bit different from the exterior. So there we have a new data type, linear ring, which is then the actual exterior, and you can then get the length of that. This is maybe a boring example as it's always the same shape, but we can try this then later with different shapes. Okay, so these are quite intuitive, easy. All of these you can find from the documentation. So there should be, for example, bounds, polygon bounds mentioned in several occasions in the Shapely user manual, which lists most of the things we cover in here as well. Okay, so we are now, that's kind of like all there is to points, lines, and polygons at this stage. Of course, things get more complicated when you have more complicated data, but this is mostly all you need to know at this point, how to construct points, lines, and polygons. Polygons are maybe the most tricky ones. Then there's the final section for geometry collections, which contains examples of multi-points, multi-line strings, and multi-polygons, so more complex geometric objects. I think in the interest of time and not to annoy the janitors too much, as we are not supposed to be here after 6 p.m. we just heard. So let's do so that we'll run kind of quickly talk through this section. You can look at it on your own time if you want. You won't be needing this now in the exercise, but there's quite cool stuff you can then do, and you will end up needing to do if you come across kind of more complicated geometric objects. So in this case, we are importing more data types from Shapely. So there's multi-point, multi-line string, multi-polygon, and box. So again, from the Shapely user manual, you can read more information about these. You can see that multi-point or multi-point is a collection of multiple points, quite logically. You can, again, either give the coordinate tuples as a list, or then the points. So I think in one exercise we actually might want to make a multi-point in order to calculate some more advanced stuff based on a collection of points. Multi-line strings, a bit similar way. So first we create line strings, and then we give a list of lines to this multi-line string. And then multi-polygon, actually here, where's the exterior? Well, you'll see once we run this soon what this actually does. But here we're kind of just creating first kind of a western box, and then a hole for that box. Yep, but maybe at this point we can just run the whole thing. So the multi-points, it's one object which contains multiple points. Multi-line, you can see that we use the same coordinate points, so it's one object with then multiple lines. There were 2 lines, so one line and the second line. The Western poly, it had, we first create just, let's read the code again. Yeah, so we first kind of create one polygon with a hole, and then another polygon using this kind of box constructor. So you can kind of create, if you get some bounding coordinate values, you can use this box method to create a polygon out of those, which is quite handy sometimes. And then we can combine these 2 polygons into a multi-polygon. That's how it went. So we have the Western polygon with a hole, Eastern polygon made out of the corner coordinates, and then those combined in one object. There's this nice multi-polygon, which is then of course more more complicated. If we look at the multi-poly, how it's represented, so there again, it already gets a bit more complicated with the inner brackets and objects in this polygon. Furthermore, there's maybe one additional useful thing we'll need later on. So convex hull, how to pronounce that? Let's Google it from Wikipedia. So it's kind of the envelope or kind of the outer bounds in a way. Let's say if we have a set of points in here. So if we would ask the bounding box, it would be like this. But then kind of then this one would be the convex hull. So if we bound the object, it's a bit different thing than the bounding box. So how to get that in Python? We had this multi-point object, which was this one. So it has an attribute, convex hull. What else are we doing in here? Then there's other tricks which I'm not now all reading out loud. Maybe just focusing on the convex hull. So this again produces, let's check, type convex. So here we created, based on the points, we created a polygon that contains all the points. So this can be useful, for example, if you have some point observations, you want to see the extent of some area, and sometimes if you just take the bounding box, you might end up with like too much estimation for the coverage. So this is another useful trick you'll actually then need in one of the exercises later on. Okay, so I think with minor technical hassle we covered most of the essential parts of kind of the geographic data model, points, lines and polygons in Python using Shapely package. In here. And then I'll still introduce the exercise, unless there's some burning questions. So I now set the deadline until, because we have the exercises on Thursdays, so maybe it's nice that you have 1 week to do the exercises after the exercise session. So next week's Wednesday would be the deadline, and I hope you submit by then. Should be enough time. If you know that you won't be able to make it, please agree with either Sakke or Sara who's checking your exercises, because then of course it's more work for us to check individual tasks from here and there, because we do it kind of semi-automatically. But if you have a good reason, then we can plan ahead and check your assignments then, for example, at the end of the course only. We're again using GitHub Classroom. I should have my exercise here already. In here, and I'll maybe now demonstrate the whole workflow to refresh your memories. So how we have been working in first period is that you first clone the exercise from the course pages, then you go to GitHub, open it, then get the cloning link, and assuming if you're working in CSC notebooks, so now I highly recommend that try to be a bit organized with your files. It can be difficult, but let's try. So under AutoGIS, we have created this exercises folder automatically for you. So you should navigate there using the terminal window. By default, when you open the terminal window, you are in the root kind of work folder, which contains the AutoGIS folder and then this exercises and notebooks from period 1. You can I don't know, you can delete them or whatever. We don't need them anymore, but if you still have unfinished exercises or want to save some notes, so good to do it now when you still remember. But we want to CD, so change directory to AutoGIS, so I can press the tabulator, not to have to type everything in. In there, I want to change directory to exercises. So now I'm located in the exercises folder. So try to do this every time you clone. So in here, then git clone. I already copied the link, but I'll just show once again from there. Shift right click paste. Okay. So you won't see your password when you type it, but it is going without you noticing it. Press enter. The screen should look like this when you have succeeded. And at this point you can list the contents, then CD exercise. And at this point git status, I'm ready to start working. If you want, you can use this Git plugin as well, but I often like to use the terminal window. So if you still, it's okay to have stupid questions about Git at this point, so do go to the exercise sessions and ask. Some of you have been lucky to run into some merge conflicts and all that fun stuff, and I hope you take that as an opportunity to learn. It's always, if you run into trouble, you can always download the files manually, go to your folder and upload the files. The most important thing is that you have your latest work somewhere saved. But then of course, if you get some tricky situations with Git, we can then solve those case by case. It's always a fun task. Then still quickly the exercise topics. So we have 4 problems for you in 2 different notebooks. I'll introduce those in a bit. Just a reminder, so we are using this NB grader for grading the tasks semi-automatically, so somebody also checks them manually. But you can always start by removing these 2 lines of code. So that's just raises an error if you never even touched the notebook. And also there are some of the cells are non-editable, so there are some little print statements or tests that should help you to solve the exercise or direct you to the correct solution, hopefully. Okay, so problems 1 and 2 are basically for you to repeat and learn the things we now discussed today. So creating basic geometries, points, lines, and polygons, and also refresh your memory about how to create functions. So you might want to visit GeoPython week 4, so you need to define functions and use the functions. So for example, in the first problem, you'll want to define a function called createPointGeom in order to run this cell without an error. So this is now a non-editable code cell. I can't do anything in there, but I can start doing the exercise in here. So you'll have to import Shapely, define a function, and use it. So same thing for points, lines, and polygons. And we also have some of these kind of, you'll have to also use some assertions. So as we learned that, for example, Polygon constructor only accepts specific types of inputs. So then you'll have to test if the input is correct. If not, then give an assertion message. So there are some hints in the hints page about assertions, and as you remember also in GeoPython, was it week 6 or 7 lesson materials, there's hints about how to make assertions. So the basic idea there was that you assert a statement, so this has to be true or false if it's false, then this message gets printed on the screen. So if, for example, the input is false, then print out that input is false, or I need three coordinate tuples in order to give you a polygon. Okay, but that's about problem 1. Problem 2 is then going further with geometries, some attributes, and so on. Maybe final reminder as we're defining functions, so also remember to add doc strings to your functions. You get also points for doing that. Then exercises, problems 3 and 4. This is maybe a bit, I don't know, a bit more fun, at least a bit more applied. So you'll have to combine your pandas skills and then your shapely skills. So we'll work with a real data file from the travel time matrix. So some of the students from Helsinki might be familiar with the travel time matrix. I'll show you quickly. So it's a data set. I don't know if there's some good image, but we have a data set that consists of, let's see if we have some image. Sorry. Anyway, we'll have kind of regional travel times from each location in the Helsinki region to each other location in the Helsinki region. That was now a poor. You can find the documentation from our research group web pages. So we have one input file called Travel Time Matrix 2015 Helsinki. In there, it's a text file. You should look at the headers, what is the separator, and read the data in using pandas. To start with, and then you will notice that, or we will use these columns, so from X and from Y and to X and to Y, so there's coordinates pairs for kind of origin locations and destination locations. So you can imagine that we will be creating some points, and then also based on these points we will be creating some lines and calculating distances. So I think this is quite a nice task. You can refresh your memory about period 1, and then also kind of work with a actually useful case with these more abstract shapely objects. And also here along the way there are some of these tests that you should be able to run in order to proceed. So I hope they are helping more than confusing you. Okay, that's most of it. And maybe one final thing before you pack and leave, now that we are so early. So just to remind you about Slack, I hope many of you have been active in there, but I still encourage you to start being active if you haven't been. And in the general thread, you should be able to click on these links and then join the channels. So this week's discussion, we can then start in here. So if you have any questions or want to share some nice stories, so ask here. So primarily, please don't send me email. I'm of course very happy to interact with everybody, but I'm very bad with emails and I never reply. So if you send me a personal message on Slack, so that's a better way to contact me related to this course. And then also if you have some questions, prefer to put them there. So maybe somebody else is faster to reply than myself or Sakke and Sara.